Well, hello, class. Today, what we are going to attempt to do is we are going to go over the first section in chapter 8. So, you guys need to read through chapter 8, pages 297 to 313. Yeah, so there's some things that we're going to kind of talk about. So, this one isn't a bad topic. It's generally students do extremely well on it. It's all this stuff about like electrons and valence electrons and all that. So, I'm just going to kind of go over some of this stuff and then you may just need to look it up in the book if you are lost. We'll do a couple of videos as well. So let's get started. Okay, so first off, let me show this. All right, we'll do it from here. Okay, so in this one, what we're talking about is, so this is called your Lewis structure. So you should know that the valence electrons are the outermost electrons. Usually they're the S or the S and P. It's never a D, it's never an F. And you should know how to do like the 1s2, 2s2 business. So sulfur, it has 16 electrons if you look at the periodic table, and it has 6 valence electrons. So you can kind of let me put this up here. So if we go to like a periodic table, a lot of this is just understanding like the group it is in structure. So this is a good review. I usually do this at the end because it's easy, and also because there's a lot of it on there. There's like almost 20% of the AP test is this topic. So I know it stinks that I'm not there, but definitely this is a topic we can do remotely, and you will have great success with this. Okay, so anyways, the periodic table shows us like how many valence it has. So group 1 has 1. These are the alkali. Group 2, alkaline earth, has 2 valence electrons, that is. And like fluorine over here, let me get my pen going here. So fluorine right here, it has 7 valence electrons, and you guys remember how it ends up being 2s2 2p5. Okay, so it has 7. Those are the 7 dot diagrams around it, and you just kind of have to understand the periodic table. So number 1, you should know like Lewis symbols, valence electrons, electron configurations, and trends. Okay, so this is just showing you the number of valence electrons and why they have the properties they have. All right, so for example, neon is super non-reactive. Okay, we call things like that. It's inert. Okay, so all right, now so the nature of bonding. So when substances combine, typically what happens is they're lowering their delta H. So like energy is delta G is like flowing out of the system. And so oftentimes these are like exothermic when things react, but they don't have to be. There can be changes in entropy that cause it to be spontaneous. But regardless, what ends up happening is the outer shells get filled up and they become isoelectronic with the noble gases. So that word isoelectronic just means the same electron configuration. So for example, Na plus, if I look at Na plus is exactly the same as neon. So neon has 10 electrons, so does Na plus. Those are isoelectronic. And I don't know if you remember the trends, but Na plus is actually smaller than neon because its nuclear charge will pull those electrons in. Remember that? Okay, so back to it. Back to it. All right, so when something does like an ionic bond, there's like a transfer of electrons. And what that means is like a good example of this would be like sodium sitting here with 1 valence electron, and then chlorine sitting here with boom, 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 7, right? So this is going to be like, hey, you take that valence electron. And what ends up happening is this becomes a positive ion and this becomes a negative ion. We call positive ions cations and negative ions anions. And usually what happens is there's a huge release of energy, and you can look up the video of salt forming from Na and Cl. Now, we call this type of bond when they form lattices. Lattices are like at the bottom of your deck. You might have like, like this kind of stuff. That's what like we call lattice. So that kind of is how things bond in ionic bonding, is they form repeating patterns like that, or crystals. So lattice energy is just the energy needed to break apart, this lattice. Now, because energy is released when these bonds are made, it takes a huge amount of energy to break those bonds and make the elements into their single thing, into the singular, just make them into single, like Na and Cl. Okay, so what ends up happening, let me go here, is this is just what I'm talking about with the lattice. So this is the solid, and the energy needed to split it up into its ions is the lattice energy. Now the trend goes like this. So if it has a strong ionic force, and ionic bonding is usually super strong, so they tend to be solid, they tend to be like hard and, they're tough, man. They're strong bonds. So, but the smaller they are, there's higher charge, and that leads to a greater lattice enthalpy. So, for example, you're going to have to do stuff like this, where you have to look and say, all right, which has a higher melting point? And LiF or LiCl. Okay, so you go over here and you look up and you find out that Cl is bigger than Li, right? So what you're going to do then is you would be like, all right, the higher melting point is the one that's smaller. So LiF is in fact has a higher lattice enthalpy, which is just a fancy word for melting or breaking apart this lattice crystals. Okay, now these ones are about the same. They're about the same size, but the difference is that this is +2. And so the greater the charge it is, the stronger the lattice enthalpy. So this would have a higher melting point. So you're gonna have to look at the structure and figure out like who wins, okay? So for example, who wins here? So MgO versus CaO. Well, you look on your table and you find out that Ca is bigger than Mg, right? They have the same charge. So MgO would have a greater melting point. That's what you do, people, right? All right, so covalent bonding is different. So in this case, what they're going to do is this is typically found between two nonmetals. So they're going to have similar electronegativities. They're not going to transfer, electrons. They're going to share them evenly. What happens with these is they end up being it's a weaker bond. So things like butter are covalently bonded, like oil, right? A lot of the gases are, so like carbon dioxide is covalently bonded. So they tend to have low melting points and are soft. And like if you think about anything that's kind of like smelly or kind of like weak, it's usually a covalent bond. Okay, so this is just something that you'll see this graph a lot. So what this graph means is like this is how far apart and how like attraction is affecting the bond. So what happens here is if the bond down here, if the atoms are too close, they're going to repel. And if they're too far, they're not going to attract. And so what the bond length is the perfect distance where you match the attractive forces of, this electron here being attracted to this nucleus right here versus the repulsion factors of the electrons repelling each other. So really, if you see this, oftentimes the bond length is just down here. You have to understand that is the lowest potential energy, and that's the maximum effect of, attraction versus repulsion. It's all about charges, which brings us to Coulomb's law. Okay, so thankfully you don't really have to know Coulomb's law, but you can. So Coulombic attraction is another fancy word for charges, and that opposites attract. So what happens in this one is the forces that are present, the bonds that are present, are directly related to two things. The first two things, and this is really all you have to know, these are the charges. So up top, the Q's are the charges. So for example, +2 has a greater effect on the Coulombic attraction than +1. That's what's going on up here. And then the bottom one down here, R, is your distance. So two factors that will affect the attraction are distance, like how far apart are the atoms, and charge. If the charge is greater, there's a greater force, and all the properties, it has a higher melting point. It becomes much stronger. And vice versa, if the atoms are super far apart, they tend to fall apart. They have low melting points, that kind of stuff. Okay. So that's what Coulomb's law is. You don't technically have to know it, but you just have to know the relationship. Charge, high amount of charge, good for melting point, really high. Low distance or short, it's really attracted. Okay, so those are what you have to know. Which brings us to the different types of bonds. So in a single bond, this is when you're sharing two electrons. This is the greatest length. And since it's longer, it tends to be the weakest. And then triple bonds, these are the strongest bonds. They're the closest. They're actually sharing 6 electrons. And so that's how you can figure out those. And so anyways, down here, the bond, like this is the strength. So since triple bonds are so close, they tend to be close together, and that's why they're the strongest. Okay, this is good. All right, so let me just mention this. So when things bond, they don't always share evenly. I believe we did this earlier. So when things bond, let's say I have HF. F is just really not nice to share with. And what happens is this gets drawn this way. This is called a dipole moment, where the electrons that are shared between F and H, F is just being greedy and it like takes way more. So this becomes negative and this side becomes positive. It's called a polar bond. So the difference between electronegativity values, and these are all found like either online or in like on your periodic table. Let me see if I can get back to it. Okay, yeah. Okay, so anyways, so what you do is, so if you want to look up the electronegativity values, let me just do it over here. You can either Google them or I'll give them to you. All right, so this is what it's going to look like. Yes. Here we go. Here's a list of electronegativity values. All right, so you can kind of see it in here. So like these are on the back of your chart too, but you can see this area right here is your most electronegative. So like fluorine is right around 4, whereas like lithium over here is like 0.96. So you can just look them up as you go. Now, what's going to happen like this is like you would have to look at what F is. So F is like 4. Whoops, wrong button. So you look up the electronegativity of F, you find out it's 4. And then you look it up for H. And let me see if I can get rid of this. So it's 2.2. Okay, so 4 minus 2.2 ends up being, what's that, 1.8. And if you're 1.7 in distance, this is ionic bonding. So I'll give you this chart, right here that has the different things listed on it. But to describe the type of bond, you subtract the difference. Let's look at O and Cl. Okay, so we're going to go back up here. Again, this is on the back of your periodic table. So it looks like O is 3.4 and Cl is 3.1. Okay, so the difference between 3.4 and 3.1 is 0.3. And 0.3, this represents a non-polar covalent bond, which basically means they're kind of sharing even. All right. Now, the O is slightly more electronegative, so it would technically, be a little bit more that way, but that's what you have to know. Okay. So let's do this. Here we go. All right, so this just shows you the dipole moment, and this is what makes bonds polar. So polar bonds are when they share electrons unevenly, and they have what we call dipole moment. This is the dipole moment is the magnitude of the difference basically between electronegativity. And nonpolar bonds, they just share totally evenly, and ionic bonding is when they just transfer electrons. Okay, it's so simple. Okay, that might be it. So as you do this, you're going to kind of read through the section in the book. You can do the Pearson work together as a team. You should be able to get it done in one of your double periods. It's due tomorrow, I believe, at 11:59. Tomorrow, I'll give you guys like a practice worksheet on like how to do Lewis structures in a couple of videos. But that's pretty much it. So take a second, look over the chapter, fill out your notes, and let's stop this video. Everybody, let's stop it. Let's see if I can figure this out. Hide, stop webcam, and